This recording will later on be uploaded to our YouTube channel, so just have to make sure that that's going. Okay, before we continue, first and foremost, I would like to briefly just introduce myself. My name is Sheryl Hermoso. I'm Network Operations Engineer from APNIC. I used to be a full-time technical trainer as well, so I'm kind of used to doing this e-learning. But this is the first time that I've done it in quite a while. Now, if you do have any questions on this session or any other topics that we do cover, particularly network security and a bit of IPv6, DNSSEC, and Internet Resource Management as well, please feel free to send me an email at cheryl@apnic.net. Now, this session will last for 1 hour. We'd like to make this as interactive as possible. So if you have any questions at any time, please feel free and interrupt me or add any pointers that you may have learned from somewhere else. It will be good for the rest of the class. But at the end of the class, there will be a brief survey just to get your feedback on how it went, and will be good for us as well to evaluate how we're doing things. But yeah, I'll give a link to you at the end of the session. All right, now moving on to the actual topic. What are we going to discuss for today? It's all about IPv6, so that the security part of IPv6, right? So to go through this session, we will first introduce you a little bit on IPv6 operations and protocols. Now, this is a little bit like if you have attended our IPv6 course previously, we will point out some of those. You might have seen some of those materials as well. However, we are now pointing out the issues that we find with those protocols. Now, it's important to be able to understand how they work, because there are possibly many issues that you can find, whether it's IPv4 or it's IPv6. There will always be weaknesses on those protocols. However, having said that, there are things that you can probably find in V6 based on these specifications, based on how it works, based on how it learns about other machines in the network, based on how it assigns IP addresses. So we will be focusing on those things for this session. All right. Next part, we'll look at some of the ways that you can scan IPv6 networks. We'll look at some examples and toolkits that are used for exploiting IPv6 and creating, those things that can perform attacks to IPv6 networks. And lastly, some best practices in securing your IPv6 network. So I hope this is something that you come for this session, okay? And I hope we'll be able to clearly discuss this with you. All right, let's begin with IPv6 operations. I hope most of you are familiar with IPv6 at this point. We know that IPv6 is, of course, 128 bits. You write the address in kind of like a different way than you write IPv4. Okay, there are differences in how you create packets. Okay, add those fields in IPv6. Particularly, we have this thing called extension headers in IPv6. Okay, what are extension headers? The way that we, the protocol, created IPv6 packets is that you have the basics of the IPv6 fields, but some of the things in v4 they don't actually need can be removed, and then later on can be added as per needed. And that's where extension headers would come in, right? So the fields that are not used regularly will be removed from the fields that are sent out often, but then added as per needed. You'll have different types of extension headers. That's a unique characteristic of IPv6. Next one, IPv6 has built-in security features. What do we mean by that? If you possibly heard from people, some of your folks, some of your colleagues mentioned that, oh yeah, you should move to IPv6 because IPv6 is more secure than IPv4. In some ways, they are of course telling the truth. That is because of IPsec. IPsec, well, it's not really just for IPv6 right now, but originally when IPsec was developed, It was to be part of the IPv6 specifications. Now, because it's taking us a long time to move into and to migrate into IPv6, IPsec has been ported to operate alongside IPv4. So it's also a layer 3 protocol. It works alongside your IP, right? Your IPv4. Now, what's the difference between implementing IPsec on v4 networks or v4 or versus v6? Is that with v6 it is part of the protocol. It's built in. Okay, it's part of the IPv6 specifications. So you don't exactly need an extra protocol to work alongside your IPv6. You can just like straight away by default it's there, it's included, it's implemented. There are options not to or to use it, but it is there. It is something that you can easily implement. Any questions on that? And the last one on IPv6 operations is it uses ICMP version 6 to discover other hosts and routers in your network. Now this thing is very important. How do you discover other networks? Okay, do you know how that's done in IPv4? And how is IPv6 different from that? Now in v4, I think we will see more of this as we go on through the slides, but just very quickly, in v4 we know that discovery is done using ARP, Address Resolution Protocol. Okay, you send broadcast messages to the network or to the link, and then waiting for your neighbors to respond to you. Now, of course, in v6, it's always going to be quite similar, but we know that in v6 there is no thing called broadcast. Okay, we don't have broadcast in v6. We have anycast, we have unicast, we have multicast, but there is no broadcast. That's another thing that, like, as part of the things that we've learned in v4, they said, okay, broadcast is not actually a good thing. We're implementing in v4, but you know there are a lot of security issues that is tied up with broadcast. If you see all of the attacks, it usually starts with sending broadcast messages, okay, that then leads to something like DDoS attack. So instead of using broadcast, they have kept into using multicast instead. It's very similar to broadcast, of course. The main difference is you're not broadcasting it to everyone, okay, even those machines that don't need to hear or to listen to what you're telling them, because they're not supposed to be part of the group that should receive the message, right? So multicast, broadcast, something that's very important in IPv6. You should know how that works. And since it's not doing broadcast anymore, therefore we cannot use ARP, because ARP operates by sending broadcast messages. And so what do we do with v6? Okay, there's another thing called NDP, Neighbor Discovery Protocol. We'll learn more about it. But as part of that, you're now sending not layer 2 messages, but this time those are ICMP messages. Okay, the things that you do, like when you do ping, right? Those are ICMP messages, and it's operating on layer 3. So in v6, okay, just learn that like it uses ICMP by default to send and receive messages to discover other machines or other hosts and routers within the network. Okay, so I hope that's clear enough for everyone. Alright, this is the IPv6 addressing structure. Just very quickly wanted to go through this because IPv6 is large. That's either good or bad depending on where you're looking at it. If you're doing scanning, is it easy to scan a structure or an IP block this big? Maybe, maybe not. If you're strategic enough, then maybe you can do it. But if you're going to, maybe your network has been assigned a /32, which is the biggest that can be received by a typical large service provider or network operator. If you have a /32, if there's an attacker that wants to, do vulnerability scanning on your network, would they just like easily scan the whole /32 range? Maybe, maybe not. Whoever is doing it, depending on their target or depending on their strategy, they might do it. But what's the consequence? can they scan an entire /32 that easily? The reason I'm showing you this is because of that particular reason, right? If you have a network, what are the sizes of IPv6 address block that you're assigning to each one? In this diagram, you notice that, as I've said earlier, you get a /32 if you're a big provider. If you're an endpoint, an insight, maybe you're working for a bank or a research network or maybe an academic network and whatnot, then typically you'll get a smaller block than /32. You'll get a /48 IPv6 block. But if you think about this, /48 it's still so much bigger than a typical IPv4 block that you will get. Okay? Now a bit more further down here you have /64, which is the prefix that you're assigning to a single link. If you have two routers, you set up a link between them, you assign a /34 block for that. Generally, only two machines or two interfaces are going to use that, but still you assign a /34. If you have a small network, a single VLAN, generally will assign a /64, regardless of whether you have 100, 1,000, or more, or even less, machines on that network. So what we're saying there is like IPv6 addresses is huge. And as much as you want to be able to know what each of your machines are doing in the network or what ports are open, what services are running, maybe for yourself or maybe from the side of the attacker, depending on where the scanning is coming from, then it is actually a hard process to be able to get all of that information. Unlike if you compare it, and you see me doing this a lot, you compare things, how attacks are done in IPv4. Maybe if you scan a single /24 block, it will take you, depending on the intensity or what you're trying to reach, you might just like take 2 hours or maybe a whole day if you're doing a lot more stuff and you're trying to get a lot more information. But for a /32 or even a /64, how easy is it to do it? Okay, probably not that easy, right? All right, so now let's look at some of the IPv6 addressing issues. Going back here just very quickly, this is your network prefix from 0 to 64. The first half of your IPv6 address is your network prefix. What does that mean? By looking at this part, you'll know what type of IPv6 address it is. It can be a link local address, it can be a global address, it can be a unique local address. So depending on what IP or what network prefix it is, it tells you whether it operates internally, it's only like reachable locally, internally, or it is global address. Say the global unicast address, maybe you get 2406.6400/32. That is a global address. You got that from, say, your ISP or upstream, or maybe from APNIC. So those are global addresses. If someone is going to attack you from outside, externally, okay, that is the IP block that is reachable from them. Now, internally, if you want to do some simple scanning for your own sake, maybe you want to also use that global address. Maybe you want a local address. Okay? So that is this part, the first half of your IPv6 address. The next one is your interface ID. How do you assign this part? It's 64 bits. Typically, it's a limitation for most operating systems. If you assign an IP address on, say, a Windows machine or a Linux machine, by default, it takes a /64. Meaning, this part, the network prefix, is assigned depending on whether it's local or global address, and this part is assigned either manually or automatically using your MAC address or a random number that is generated by your operating system. So that 64 bits is your interface ID. Now, why is this important? Because there are two ways in which you assign this. One is, okay, well, you can do manual, you can use DSGP, but the two most common ways to assign this part is, one, modified EY64, and the next one is privacy address. So let's look at modified UI64 first, okay? Now, when you enable IPv6, and when you get an IPv6 address, and by default it uses modified UI64, what happens? You get the network prefix from your router, okay, and then the 64 bits is assigned by your machine. When you say modified UI64, it is based on your MAC address. So your interface will have a physical address, and from that 48-bit physical address, it will generate a 64-bit interface ID, right? So that is your interface ID based on your MAC address. So imagine the scenario. I am working at the APNIC office. Okay, I'm connected to our wireless infrastructure. Okay, our Wi-Fi is, or our router within the Wi-Fi network is providing a network prefix. Okay, and then from there, I get my IPv6 address. So imagine me moving somewhere else. Maybe after this, I go home and then I set up or I connect to my own home network, which also has IPv6. Then I will get another IPv6 address. But notice, my interface ID will be the same. My network prefix part will be different because I'm getting a different network prefix from two different routers. Now imagine me moving from those two places, maybe traveling to Singapore or to Pakistan or to Hong Kong or China. Same thing, right? If I connect to the IPv6 network, I will get an interface, a network prefix that is different from my previous network that I'm connected to, but I will still be using the same interface ID. So that is an issue, right? For some people, that's okay, but for security folks, they think that it is a privacy concern. That's actually why privacy address became a thing in v6. So that's like an alternate way of assigning IPv6 interface ID. Because some folks are not comfortable with having their MAC addresses, exposed by moving to different networks. So that's the second one, right? Privacy address. How is it generated? This time, you're no longer going to depend on your MAC address because MAC addresses, by moving from network to network, is trackable. If you do privacy address, by default, your operating system will now generate a totally random 64-bit number that you will then use for your interface ID. Okay, so that's the thing with v6 that you have to be also aware of. Are you going to use UI64? Are you going to use privacy address? By default, most operating systems, I think the newer versions, say Windows, I think from Windows 7, also Linux, are now using a privacy address. If you want to keep using UI64, it's always still possible. If you are using UI64 by default, there is a way to use privacy address, just not default. I think that's the case with most Mac OS X systems. But please verify your operating systems and have a look. Try to maybe investigate a little bit on the functionalities of v6 and observe how it's working for you. All right, next one. Scanning IPv6 network. Okay, there's a question there from Arpan. How do we do that in Mac? I see that my IPv6 is using my MAC address right now. I don't have a command here with me. I'll just send it to you. But yeah, by default with Macs, it's using EUI64. Okay, so but yeah, Arpan, I'll send you an email later because I don't have it the back of my head right now. It's hard to type. So I'll just send you the commands when I get the chance. I think I know your address if I remember if it's actually, or type in your email on the chat and then I'll send it to you. Is that okay? That'll be easier because I don't have it memorized me. All right, cool. Thank you for that question, Arpan. Any other questions from the class? So we're good? So if you are implementing IPv6 in your network as an enterprise perhaps, just make sure of this one thing, maybe something that you can easily add to your IPv6 requirements or IPv6 policy, whether you're going to keep using UI64 or a privacy address. That depends on you. For me particularly, I don't have an issue with using EY64, but there are some folks that are sensitive to this information. Right? Next one, scanning IPv6 networks. I have briefly mentioned about this earlier by looking at the entire IPv6 address space. We know that you have 128 bits, which translate to about 4.3 billion addresses, which is a lot. Compared to your IPv4 network, you normally get possibly a /24, a /21 IP address, which is much easier to scan. So this goes both ways, right? For some people, they were like confident that, okay, I'm safe. I'm using IPv6 right now. I can put up firewalls, I can put up ACL, but what's the point? It is too big for someone to scan this network. So just by obscurity, I'm actually safe. Okay, that's a mindset. I know if you're careful, you don't want to do that, but that's a typical mindset for most people who are just starting up with implementing this. So sometimes it takes a long time to scan if it is a really big IPv6 network, right? But if you look at different factors, if you look at patterns, it is possible to scan them. Why? First of all, how do you assign IP addresses? How do you plan your IPv6 network? If you look at different cases of IPv6 implementation, you know that most of them follow some pattern when they're assigning. Say, for example, from their /32, you divide that into your /48s, right? From that /48, if I'm a network operator, for my backbone network, I will use the very first /64 out of that /48. From that alone, I know that I can start, okay, you have a /32, but it doesn't matter. I will start scanning with the very first /64. If it's still too big, from that /64, actually, most people will start with colon 1, colon 2, colon 3, etc. So you start there. Maybe you want to find the first /120, okay, which is 2 raised to 8. That's already 256 IP address equivalent to a /24. So you can start by doing that. So basically, what I'm saying here is there are ways to find patterns when you're scanning network. Even for some tools, even if you give it, say, hey, this is the /32 block, then they will intelligently just look for smaller blocks out of that /32 so that you will have quicker scans and most likely you will hit targets. Okay, so just be aware of those IPv6 addressing issues. Another thing that you should be aware of is the extension headers. I know I pointed this out at the very beginning, but let's look at this in more detail, shall we? So what are extension headers? Extension headers are kind of like, you can think of it as add-ons. They extend your IP. It's something that you insert into your IPv6 header to add functionalities to it. Okay? For example, look at the diagram on the right side. You have IPv6 header, right? And the next header points to your TCP. This is your typical IPv6 header. Nothing, no extension header in it. However, if you're going to add extension headers, there's actually no limit. You can insert your extension header. See this? You have 1, 2 extension headers in between your IPv6 header and your payload. Okay? Now, when you look at the IPv6 specifications, you'll notice that the number of extension headers are actually not fixed. Meaning you can have 1, you can have 2, you can have multiple. The total length of the extension header is variable. Okay? So you can, maybe you have 5 routers, maybe in router 3, it will receive a packet that has 100 extension headers, which might have an effect on how, or the speed that it processes the packets. Okay? Another thing to be aware of is the order that extension headers come in. there is a recommendation set by the RFC, meaning the extension headers that will be read by each point as it hops going to its destination. Let's just say I'm hopping, my source is network A, my destination is network E. So I'm hopping from A to B to C to D to E. So the headers that has to be read at each point from B to D, it has to be added closer to your IPv6 header, meaning it has to go before the others. Whereas the extension headers that will only be read at the very end, meaning at the destination at network E, will have to go a bit further in. So kind of like stack, you pop the extension headers. The ones that will be read at every step will have to pop in before the rest. Okay, so yes, that's good. However, as you can see here, it is a recommendation. There's no particular requirement, so it is up to the vendors, the providers that implement these hardware that has IPv6 support to implement it as they wish. So in some cases, if you stuff up these headers, it might cause issues. Maybe the network cannot, the routers cannot read it, or it's stuff that like it will cause chaos. It will use up a lot of memory, a lot of like CPU on the machines and things like that. Okay, so just be aware of those limitations on extension headers. One, no fixed size, meaning you can have one, you can have 1,000 extension headers. No limit. And the next one is no particular order as to where or when these extension headers would come in. That results to these kinds of attacks. Extension header threats. They could do the following things. They can create an IPv6 packet with a long list of extension headers. Imagine that if you have 1,000 extension headers and you have 1,000,000 packets being read by your router, say 1,000,000 packets per second, each of them having 1,000 extension headers. What can be the result? DDoS, right? So you're DDoSing the router along the path, or maybe it's going straight away to the destination host, depends what you're trying to target. Next one is lengthy extension headers. So there's like a long list of extension headers. It can consume system resources. It could cause your host or your machine to crash. And the last one, it could be used as an attack vector to inject malicious code. And this is something that you should be wary about. You say that this extension header is a routing header, for example, or a fragmentation header. However, the content may just look a similar format as your typical routing header, but may contain malicious code. That's always possible, right? So what happens here is, because it is acting as if it's say a typical extension header, it can avoid or it can pass through typical firewalls and intrusion detection systems. Okay, so just be careful about these things. Now, we've talked a little bit about possible issues, with the protocol, but let's focus on the positive side. What are the security features that helps IPv6 to become more secure than, say, IPv4 or other types of protocols? I've mentioned a little bit about this earlier, and it's called IPsec. IPsec is mandatory in IPv6. It's already part of the IPv6 protocol stack, meaning just one specification, one protocol can implement the security functions that you wanted to protect or encrypt your data. One thing that makes IPv6 good is using IPsec, you can have or you can enable end-to-end security. From my machine, if it's sending or if it's communicating to your machine, all of that traffic end-to-end from my machine to your machine, is all encrypted. So all the paths that it has to go through, okay, you're kind of like confident that your data is secure and it cannot be read by all of those machines or all of those routers in between. Okay, IPsec, however, be careful about this part because again, some people think that all right, you have IPsec and IPv6, you're secure now. You don't have to do anything else. IPsec does not replace the standard network security requirements. As we know, there are many stacks, many levels to your IP security, not just IP, so your protocol stack security, and IPsec or IP layer security in general is just one of them. You still have to add security measures for all other levels of your protocol stack. Okay? All right. Now here, I'm going to focus on neighbor discovery protocol because we know that the way that you discover other machines in IPv6 is a bit different than IPv4, and through this actually, it is prone to some of the attacks. Similar to the, if you talk about L2, L3 operations in v4, okay, if you've seen some of those attacks, like layer 2 ARP related attacks, or ICMP related attacks. There are similar things in IPv6, but this time focusing on neighbor discovery protocol. Okay. Oh, so IPv6, we already know that it uses multicast instead of broadcast. Okay. NDP or neighbor discovery protocol. Okay. It's operating on layer 3, not layer 2. So it uses ICMP v6 for transport. Okay. So there is no need to write different ARP for different L2 protocols. It's just all using layer 3 ICMP. Now, there are many things that you use NDP for. They're all part of the neighbor discovery protocol, of course, but just terminologies as to its functionalities. One is SLAC, stateless address auto configuration. How you assign an IPv6 address on your machine. How do you do that? It's done in a stateless manner. You can have an IPv6 address automatically, but it has to go through some process, meaning it has to discover whether this IP address is already in use or not before it can be assigned. So to be able to do that, it uses NDP. Okay. Next one is discovering other machines and other routers. So we call that as neighbor discovery and router discovery. Neighbor discovery uses neighbor solicitation and neighbor advertisement. Router discovery uses router solicitation and router advertisement. And the last on that is your duplicate address detection or DAD. So I guess in some ways it's similar to, it's part of the functions of these first two. However, this part tries to find out whether an IP address is already in use or not, whether there is duplicate before you actually allow the IPv6 address to be used by your machine. Okay, similar to v4, you need to have unique IP addresses. Okay, all right. These are the different NDP messages. Router solicitation is 133. 134 is router advertisement. 135 is neighbor solicitation. Neighbor advertisement is 136. And we have another one called a redirect. Redirect in v6 is similar to redirect in v4. But the first four here are quite unique in v6. Okay? The names itself are self-explanatory, right? For router solicitation, you're trying to look for routers. Okay? Why do you need a router? To get an IP block, to advertise an IP block that you can use for your unique local address or your global address. Router advertisement is coming from the router. After you send a router solicitation, it will respond with an advertisement. Okay? Now for neighbor solicitation and neighbor advertisement, that's in between machines. Okay, how do you find and send messages to these machines? Or again, for DAD, if you want to see whether other machines in your network is already using that IP address. Now, why is this important for us? First and foremost, we know how to use ICMP in v4, right? Pretty straightforward. Usually, it's used by administrators to look for, say, basically to port networks, to probe networks, to find out, okay, is this network up? Is this machine up? Can I reach this machine? Right? So we use ping typically to find out whether a machine is reachable or not. So in V4, we tend to have limitations in ICMP. Generally, as a best practice, you only limit, say you have a network operation center, or maybe you have your VLAN that is used by your backbone machines, backbone networks. You generally limit access to them from some networks only. So ping to those machines are not allowed unless it's coming from this network or this VLAN or this IP addresses, right? Now in V6, we have to be a bit more careful with that because as you can see here, ICMP is largely used by NDP. Okay, it's not just for reachability anymore. It is used to actually find and communicate with other machines. So it is I guess in a way, it sounds a bit more important than its function in IPv4. In V4, it's a bit more just auxiliary. Okay, just do it for like for checking network for reachability. Whereas for V6, it's more important, and not doing so will have a bit more consequence. So so how does it actually work? So like this, when you have a network turned on, let's see, there you go. You perform duplicate address detection before you assign this IP address. Check whether it is a unique address. Send neighbor solicitation to a multicast address, in this case FF02::1, which is your all nodes multicast address. And then if no response comes, which is the neighbor advertisement, then it is unique. Then that's the time that you can assign it to your local interface. Same thing happens if you're assigning a unique local or a global address. You send for a router solicitation. Okay, look for a router to give you an address. Okay, you're sending it to our on all routers multicast group FF02::2, and then wait for a response from a router. That's your router advertisement. It gives you the address. You will learn the network prefix only. Okay, notice you're only getting the network prefix, which is this part, right? And then you will assign the new address using the network prefix learned from the router and the interface ID. So notice that for your link local address and for your global address, the last 64 bits, which is this, is the same because that's your interface ID. Okay, so that's just a background. It's not security yet, but where's the security part here? Here, NDP attacks. So you know how it works. Now you can see some weaknesses on that. What are those weaknesses? You can send attacks like this. For neighbor discovery, you can do NDP spoofing. You can even do a denial of service attack for duplicate address detection. For router advertisements, you can do RA flooding, or a machine or router can act as a rogue and then send false route advertisements or RAs. Note that if you look at that link that we have there, anyone can send an advertisement. So whether it's a neighbor advertisement or a router advertisement, anyone can send those. If you're a typical Linux machine, it can even act as a router and then send route advertisement, not just neighbor advertisement. Right? So what I'm saying here is if you have a network, if someone just like connects to that network, they can easily falsely act as a fake machine or fake router and send false information onto that link. Okay, something again to be aware of. Not that you would want to use these things, but these are just for your familiarity. These are some of the attack frameworks in IPv6 that have been out in the wild and that's being used. They're all open source. THC, probably one of the first few ones that we've seen out there. SI6 also has their own IPv6 toolkit, and this one, Chiron. I have personally haven't used that last one, but typically they all have similar functions. If you want to, or if someone's sending an attack, they will use one of those toolkits. What types of attacks we mean there? It can be different things. It can be someone spoofing an IPv6 address, let's say alive6 or parasite6. Someone that redirects your traffic somewhere, that's reader 6 in this case of THC IPv6. Someone that can pretend to be or perform functions such as ACLs, firewall, someone that can pretend to be a fake router, etc., etc. So you can have a look at this tools out there and see how and what types of things that it can do. So these are some of the commands it can do. Now I'm just showing you this as a kind of like a proof of concept in a way to show you that those NDP attacks actually exist. So I'll skip this for now. We've kind of touched this earlier, but this is like ways in which you can easily scan IPv6. If we have enough time, I'll go back to that slide. But right now, let's show examples on using those toolkits to perform attacks over IPv6. Here I'm using two tools in THC, I think. One is DNSDIC for dictionary, which means they're looking for all subdomains, enumerating all IPv6 addresses on the network by using querying your DNS servers. And then the other one is looking for live machines on the network. So the information that you get from DNS will be used to check which ones are alive or not. Now, please don't use this. This is just like for an example, okay? But try to run it onto your own machine, for example, or a trusted environment, and notice that you can actually find live IPv6 machines on that particular segment, which makes it easier to do scanning. Okay, so remember here, you don't have to scan the whole /64. Instead, you do something like this, and you now have a small set or a small subset of your /64 that you can do more, targeted either attacks or scanning. Now here is an example of duplicate address detection. Now you know how that works, right? You're looking for a machine, looking whether that IP address is in use so that you can use it if no one else in the link is already using it, right? So you're checking whether the address is unique or not. Now when you send your neighbor solicitation, what happens is if you have a fake machine here, an attacker, every time that you send a neighbor solicitation, it will respond back with a neighbor advertisement. Regardless of what IP address you're trying to look for, it will always have a neighbor advertisement response. And that is done here. See, you're spoofing an IP address, so and whenever you receive a neighbor solicitation, we will respond with a neighbor advertisement. This is a denial of service attack, right? Because that machine cannot have an IP address, cannot get an IPv6 address because it will keep on changing IP and checking whether that's available or not. And every time it's being blocked, okay, because of this duplicate fake advertisements. Another one is neighbor discovery spoofing. With neighbor discovery, you're looking for other machines in the network. Like in ARP, you're looking for which MAC address is this? Same thing with neighbor discovery. Which host lease MAC address? What is host lease MAC address? So you send a neighbor solicitation again and wait for a neighbor advertisement. Now this attacker is spoofing that IP. So it will respond with an answer saying that, hey, this is my neighbor advertisement, this is me, you can send messages to this MAC address, when apparently he's spoofing that MAC address, and so he's not the actual recipient. If you're sending messages in clear text to this machine, then you're in a lot of trouble, right? Next one, another example here. This is an implementation of NDP spoofing, the diagram in the previous slide. This is an ARP spoofer for IPv6. So again, you're spoofing, but in this case, just layer 2, which is MAC addresses. So you keep on responding with fake MAC addresses on these machines. Another one, rogue route advertisement. If you want to have a network address, right, you're going to send a route solicitation waiting for a route advertisement. Okay? Now, what if, suppose this is your router, the one in the middle, but for some reason, there's another one that connects here, which is your fake router. And when you send your router solicitation, it also responds back. Okay? All hosts auto-configure IPv6 based on this spoof route advertisement. What does that mean? That includes default router. That includes the IPv6 prefix. Meaning, your traffic will not have to go via this fake router. That will be your gateway for this network. Okay? So again, if you're passing through that, that is like man-in-the-middle attack. Maybe he will read your messages. If it's not encrypted, then they can find that information. Okay, now this is still similar to that one. Attacker is intercepting, listening, and modifying the packets coming from host A. So ideally, your packet will just be coming from here, going to your default router, and going out to the internet. But since now your default router is this, traffic will go via this attacker, and then maybe this attacker will redirect that to the actual link upstream going to the internet, or maybe not. In this case, if it's going up to this point to the attacker, then it's like you don't have network, but still you're sharing that information, that data has already been intercepted by the attacker. So that's an example of a rogue RA. Any questions on this? So how is it implemented? Is it just theory? Actually not. This example in the PHC toolkit does exactly that. It acts as a fake router. Notice here, this is my machine in the network with a fake router. So the fake router advertises multiple prefixes onto my machine. And notice that I have a lot of IPv6 addresses. Each of them uses a different network prefix. One of that is the prefix from the fake router, which is 201D35D, which is this one. It's highlighted. Okay, so most likely this one is my real or the correct default router. But notice that some of my traffic can pass through this, because I have this IP address, can pass through the fake router. Okay, is this clear enough? Do you guys get this? Another one is RA flooding. So you can think of it as like in V4 you also have ICMP flooding and things like that, right? You can do the same thing in V6. RA flooding is one of them. What does RA flooding mean? You're now sending or flooding the network with multiple route advertisements for multiple prefixes. And look at what it's doing. This is my victim machine. I now have multiple IP addresses. Actually, it's longer than this. It's longer than this. That's because when you look at this attack, each of this dot is actually 1,000 packets. So I'm sending heaps in here. So it only takes a few seconds, and I'm already sending multiple, okay, flooding multiple messages to the network. How does the fake router reply to router solicitation when there is the real router in place? That's a question by RFAN. It's just a case of anyone who receives router solicitation will respond. When you send a solicitation, whether it's neighbor or router solicitation, it goes to a particular interface, right? All routers or all nodes. So all routers, if you have an actual router or if you have a fake router, regardless, all of those are listening to that particular interface. a multicast address. In this case, for all routers, generally it's FF02::2, right? So whoever is listening there will respond. It doesn't matter who gets there first, whether you have a real router or will respond, your machine will accept it. Your machine will use that network prefix and assign an IPv6 address. If you have a fake router, it will still respond, okay? And then your machine will still receive it, will still accept it, and assign an IPv6 address based on the network prefix. That's why here you can have multiple. Maybe some of these are coming from the real routers, some of them are coming from fake routers. So you get the point? So essentially, anyone who's listening on that multicast address, that's like typically for the routers, can respond with the router advertisement. And since by nature, a machine can have multiple IPv6 addresses, right? All of these are acceptable IP addresses for a single interface. That's the nature of IPv6. One interface, you can have multiple IP addresses. One to many link local, just one link local, but one to many unique local and one to many global addresses. So all of them will be accepted by your router. By your machine. Does that answer your question, Arpan? All right, cool. Thank you for that. Any other questions from the class? We still have some time. I think I'm almost at the end of this session. But this is just to show you that these attacks are real. These attacks can actually happen. And so what can you do on your end? You have to be pretty careful. In the same way that you are careful or you perform different things to add security on your IPv4 network, the same precautions should be added on your IPv6. You cannot be comfortable enough saying that, okay, it's fine because I cannot be attacked. It's too big for them to scan my network. Okay, you have to add security measures. You need to have security measures in place. These are ways to detect rogue RAs and ND spoofing. Most of those attacks can actually be prevented. Okay, I've shown you that it's real, that it can happen, but the good news is it can be prevented. Generally, if you have a powerful enough intrusion detection system and updated enough that supports IPv6, they should be able to detect these types of wrong or fake information being sent on your network. Why? Because they should already have signatures from previous attacks that's added onto their database. They should have sensors in different segments that can trigger alarms when this is happening. Another thing is, say, NDP1 can also do that in most of the cases. There are others that were used in the past, although they're not quite as popular or not used that much anymore, and they're already deprecated. Raymond-D and RA-Fix-D are some of them. This is if you're implementing it on, say, a Unix or a Linux machine. Another thing is the RA guard. So router advertisement guard. So look for it. RFC 6105. What it's doing here is you will have an L2 device in the middle. So all messages between your endpoints, say host, router. All messages, route advertisements coming from these hosts going to your router will have to go through your L2 device. So what's it doing is just typically filtering messages. Okay, RA messages will have to go through this device, and it will only be accepted if it's coming from this particular router. Okay, so that is the purpose. So, but you have to have this machine sitting in the middle of your network, okay, to do the traffic and like dropping packets, for example, if it's not coming from the correct or the acceptable machine, in this case, your actual or your real router. So that's RA guard, something that you can implement on your network. But the downside to this is, of course, this L2 device. It's for some cases, for implementations, it might be too much to have something like this particular setup. There are three types of RA guard. We don't have time to cover all of these here, but have a look yourself. Stateless RA guard, stateful RA guard. And the most common, probably the one that is I would recommend, is send-based array guard. So it's filtering arrays based on send consideration. Now, what is send? Send is secure neighbor discovery. So look it up. It's RFC 3971. It's a crypto solution for securing your NDP messages. So what's happening here is you will have this NDP message. Okay, it looks very similar to your typical messages. You have your IPv6 header, you have your next header, you have your extension headers, and as additional to that, you have ND message specific data and options. So this is additional options that are added when you are sending your packets. So they can verify that it is this message or this particular packet is secure. Okay, so basically, instead of having something like this, let's go back there, something like this device that does the trafficking for you, you will use crypto to make sure that you're sending the correct messages going to the correct destinations. With crypto, you can verify that it's coming from the correct destination, right? Or, sorry, going to the correct destination. And if it's like in between your host and your router, you can use that to verify that you're receiving and sending correct information to them. So that's one way. You're using cryptography for that. Downside to using this might be additional resources used, because again, you're using crypto to encrypt, decrypt, and things like that. So that's one of the downside of using SAN. But otherwise, I think it's a good thing to implement. If you have a powerful enough router and it has support for this, it is really, it is doable. It can be done. All right. Next one is IPv6 filters. Okay, we're nearing the end of this presentation, but just before we end, I'd like to also have a look and check whether you have filters in place. This is very similar to how you think about like V4 filters, right? You should filter out different types of ICMP messages. You should have rate limiting. If you're still using routing header 0, this is already deprecated. But if just in case you're running a very old system, you should have to use no IPv6 source route. But most of the machines and routers do have support for this, and it's now the default configuration since RFC 5095. Another one is route filtering. Again, very similar to how you will probably do things in IPv4. With ICMP filters, the important thing to understand here is which ICMP packets should be acceptable or not. Should you just drop all ICMP packets or not? Look at RC 4890. It has really good recommendations for filtering ICMP-v6 based on which ICMP-v6 types are being used and not. If it's not in use, or it's undefined and allocated for experimental purposes, then it may be okay to block them. These ones as well, they're not used for any specific purposes. They're usually blocked through network perimeters. If you have type 138, 129, 139, and 140. So basically, all these red ones are generally safe to block. But again, if you have a different circumstance, you might want to just double check if you should or should not block these prefixes or these ICMP-v6 types. In general, you should always accept type 1 to 4 and type 128, 129 ICMP-v6 messages. Okay, generally it should be accepted. Another one for rate limiting. Rate limiting ICMP-v6 traffic. This is just an example of how you can implement using policy maps. If it matches any IPv6 protocol, okay, goes through access group ICMP-v6, and notice that you have this policy that only allows certain number or number of packets going to your interface FA00. So essentially, you're preventing possibly a denial of service attack by limiting the number of acceptable packets coming into your network, your router, through rate limiting. Okay, so this is an example configuration, I think, for a Cisco router. Yours might be a bit different, but at least you have some idea that it can be done. You can do rate limiting in IPv6. Another one is bogons, Martians, and things like that. You should know that concept already in IPv4. We have the same in IPv6, right? You can do, what am I doing here? Prefix listing. So you have a prefix list. You're getting a set from, I think you have BGP peering with, this one is Team Camru because they kind of like host an updated version of all the bogons list. So you can do peering with them, and then it will have like a local copy of those updated bogons that you can easily just drop from your network. So kind of like having ACLs and filterings for that. Another one, this is a recommendation from, okay, I think this is also from Team Camru, so do check out their site. They have some really nice stuff. So some recommendations on what IP prefixes you are safe to block or drop by default. We have to be careful at some stage because some of these IP addresses may be used at some point in the future, but just make sure that this is updated. But as of now, if it's default routes, all the reserved IP addresses, and specified loopback addresses, you can generally safely drop them from your border routers. So have a look at this. Generally, these are special use prefixes that you can easily drop. Another one is to reject your own prefix, right? That's pretty straightforward. Even in before you do the same thing. So you can still implement the practices that you do with route filterings as you would in your IPv4 network. Okay, so just to wrap things up, IPv6 security practices. First of all, check if you're running IPv6. Why am I saying this? Because most people, I hope this is not the case anymore, but for a very long time, some people are like, okay, I don't need it because I'm not using IPv6, okay? But actually they are, because things like tunneling, Teredo, and stuff like that that are supported by a lot of the operating systems from even 10 or 20 years ago, they do have this. They can use IPv6, you can use tunneling via v4. So in your case, whether or not you're doing IPv6 intentionally or not, just double check whether you are running IPv6. I hope you are running v6, of course, but when you do, make sure that you have the security measures in place. Learn IPv6, we've done a little bit of that. If you want to dive deeper, please do so to understand how it functions and what are the things that you can do to prevent all those like weaknesses that we have found out with the protocol. There are already countermeasures or security practices that can help you deal with them. So it's just a matter of you learning and implementing them. Next, adapt similar practices as you would in IPv4, things like VCP38, URPF, prefix filtering, source addressing, right? Basically, you can do similar practices in v6. If you have IPv4 policies in place now, replicate those policies in v6. Next, check if your security equipment supports IPv6. I do hope that whenever you purchase a new machine, a new router, a new equipment, a new security device, make sure that it has support for IPv6, okay, and has security support as well, like those RFCs that we have mentioned, should all be supported on your device, on your equipment. And lastly, always include security in the overall IPv6 deployment plan. Some of them leave it at the very end, like don't care about it until it's all implemented, which makes sense because some people, the implementation part of v6 is already overwhelming enough. But it's always best if we have all of that in one. So if you're just starting planning your v6, make sure that you have, included in your documentation, your plans, you have security. How are you going to secure once you have deployed them? Okay, how are we going to secure these servers? What are the configurations that I need to add on my border routers, on my um, distribution routers, etc., to have not just support for V6, but security, V6 security in there as well. So that's pretty much what I have there. I've actually talked a bit too much, but if you do have questions, please feel free to still write them on the chat. Otherwise, this is the link to the feedback form. Please take a couple of minutes to just fill this up. I would very much appreciate if you can give us feedback on how we've done and what else can we do to improve, particularly this course. If you are looking for something else that we haven't covered, please mention that in the feedback. So this is the link. Please go to this one and let me know. Let us know your feedback. Another one is the slide handouts. If you want a copy of this one, it will be available on our FTP site, so ftp.apnic.net. I'm not sure if I have uploaded it yet. I've done this in a while, so let me just quickly check. Alright, it's not there yet, but if you check a little bit later, I will upload it onto this link. So again, if you want a copy of the slides, it will be uploaded on the FTP page that I've just typed in onto the chat. So there you have it. I think that's where we will end the session. Thank you very much, everyone, for your time. That's like 1 hour of your time. I hope we made good use of it, and I hope you learned something from it. Please send me an email if you have any other questions. Arpan, I still owe you, I think, some information that I have to send you as well. But everyone else, thank you very much for your time.